It is our great honor to invite Saikat Dan to join our this and give our presentations. Before he starts his talks, we would like to have a short chat with Saikat. As I know, Saikat recently graduated from a computational mechanics group and joined industry companies. Can you have a brief introduce about your current jobs to us?
Yeah, sure. Hi, Anrang. Nice to meet you after a while. Yeah, so currently I work for a company called Third Wave Systems. It basically specializes in providing machining solutions. So basically develop software for machining applications. So metal cutting essentially. So I typically work in the software development team. So my role is basically developing software and improving already existing software for simulating metal cutting kind of applications. So yeah.
That sounds pretty cool. And what do you think the biggest difference between your previous research as a graduate student and currently computational works at a company?
Well, previously the work was very focused into research. So you would spend a lot of time like trying to understand the every detail of the process. However, in industrial research or industrial job profiles, you don't have that much of flexibility. So you set your goals according to the time or the resources available, and then you try to achieve that goal. You break down the problem a lot more than what you would do in a academic research setting, because you do not have as much resources as you would in an academic environment. So yeah, I would say that's the main difference. You are expected to not fail as much as you would have been expected in an academic setting. So yeah, you have to be really careful about how you conduct the kind of research that you do. So yeah, I would say those are the two main differences.
Yeah, that sounds pretty nice. And do you need to often go to the companies every week?
No, not really. So my job is completely remote. So I work from home. We do have like company meetings twice a year. So that's when we like all employees go to the office and meet up and then have those meetings. So yeah, it's mainly like twice a year when we have to travel to office. Other than that, there are a couple of conferences that you might need to travel. So it depends on that year's particular funding situation and all of that. So yeah, so that's all the traveling that you have to do. But majorly for my profile, it's like remote. So I'm based out of Maryland itself. Yeah.
Oh, that sounds pretty cool. Like a perfect work for choice.
Yeah, yeah.
And
Exactly.
how do you feel about the remote works?
Uh, I honestly like the remote setting. I feel that I waste less time as compared to I would have if I had to go to office with the travel and with the traffic and everything. So I honestly feel that I utilize a lot of my time properly since I'm working from home, and I am already in that space in my mind that I can really just wake up and start working. So I really like that idea.
Yeah, I agree. That is a perfect lifestyle. But does your company still hiring these years?
Uh, it is, but the profiles that I think the companies right now looking at is not very research oriented. So it's mostly applications related profiles. But yeah, let's see. Probably in the future, we'll open up some more like computational mechanics kind of roles.
I see. And as I know, before you go to the US, you already have a job. What make you
Yeah.
decided to start your graduate studies at that time?
Well, I really wanted to experience the kind of computational intensive profile that I wanted to do. I was not actually into a lot of computation before coming to the US for my graduate studies. So I really wanted to explore that. And yeah, that's how I started working in this. Yeah.
Yeah, you already did a good job in the computational mechanics. And as you already get a degree, do you have some suggestions to the current or the potential graduate student in the computation mechanics area?
Yeah, I tell this a lot of times that in the academic setting, don't be afraid of failing. I would like suggest that you fail more than you actually get good results. That makes you learn a lot of things. And yeah, try to learn as much as possible, because that's going to be useful for the rest of your life, whether you are in the academic setting or in the industrial setting, doesn't matter. But this time that you give to your graduate studies, maybe like 5 or 6 years, try to learn as much as possible, and just not focus on your problem, which you will do anyway, but try to learn outside of your niche domain. I would really suggest doing that.
Thank you so much. And now you can share your screens.
Sure. So
Yeah, and in the meantime, I will have a short disc introductions for our speakers. Now Saikat Dan is a computational mechanics engineer at third wave system companies. He works on improving their mechanics modeling software with his expertise in finite element analysis and material modeling. Before he went to the graduate school, he worked at the Research and Innovation Center at the Indian Register of Shippings. At that time, he developed numerical methods for the large-scale analysis of marine and offshore structures. He earned his PhD degree from Johns Hopkins University in civil and system engineering 2 years ago. His graduate research focused on developing digital chains for damage analysis in piezo-composites across different length scales. He has received many student awards for these works, such as the Best Student Posters in Engineering Mechanics Institutes and the Multi-Scale Material Modeling Conferences. He was also recognized by the American Society of Civil Engineering and the International Society of Materials Modeling. And now it is your screen. I will mute myself. Thanks again for the presentation.
yeah, thank you. Thank you for that introduction, Yanrang. Yeah, so today I'll be talking about part of my PhD research, which focused on micromechanical modeling of fracture in piezoelectric composites. So first and foremost, I would like to acknowledge the efforts of my colleague Preetam Tarafdar, who is now in the industry again. So he works for Goodyear right now, but we started this project together as graduate students. And of course, my PhD advisor, Professor Somnath Ghosh, who has been very instrumental in this research, as well as the funding agency, USAFOSR, for providing the funding. So this topic, basically, I would like to start with the motivation for this problem. So when you think of composite structures, something that comes to your mind is like an aerospace structure. So in aerospace structures, you typically have fiber matrix kind of composites that are made that are used to make the structural frames or the fuselage of those large scale structures. They are typically very prone to different fracture mechanisms, different failure scenarios that happen. So typically, matrix cracking, fiber matrix rebonding, or fiber breakage are the major failure mechanisms in such structures. This is an area of concern, specifically for such structures which are required to be designed in a safe manner, and the safety is of concern. So typically, the way you would sense the state of damage in such structures would be in a post-mortem phase. So when the structure is not in operation, you would typically attach sensors and then pass in some kind of a signal. Could be like microwaves or X-rays, And that basically tells you about the health of the structure. So that's what typical structural health monitoring processes are carried out. But these large-scale structures often initiate damage in these large-scale structures often initiate deep down into the microstructure, or even deep down into the structure, which is not quite accessible in terms of, let's say, visually accessible, or your external array of sensors or the machinery is not able to access such locations where the damage might initiate. So the typical shortcomings of this kind of a situation is that you, first of all, you are attaching sensors to the structure that is affecting the operational requirements of the structure. And since you are attaching sensors only in a limited area of the structure, so it allows limited damage sensing capabilities. The solution that we wanted to propose for this is the use of piezoelectric fibers instead of passive fibers like glass fibers that are typically used in such composites. The use of piezoelectric fibers offers a dual functionality. It does not compromise with the structural integrity in the first place. And on top of that, it also allows you to perform damage sensing. Because these are piezoelectric fibers, any kind of mechanical loading, it is going to respond to that mechanical loading in the form of electrical signals that might come out of the structure itself because of the nature of the material itself. So it provides you like a built-in virtual damage sensing capability over the entire structure, since the entire structure is now made of piezo composites. So the problem computationally or physically is has pretty nice characteristics. So first of all, it's you have very brittle or very hard fibers embedded in a soft matrix. So it's a finite deformation problem because the matrix is going to deform a lot given some kind of external loads. Given that the fiber is piezoelectric, the problem is now coupled because the deformation states are coupled with the electrical fields. And therefore, this has to be a multiphysics kind of a problem that needs to be solved. And again, damage monitoring is something that can be done now, because what happens is now, given some kind of an some kind of a mechanical loading onto the structure, it responds in an electrical way. So it gives off an electrical signature from the structure itself, from the microstructure itself. So it allows you to perform damage monitoring. This entire process is divided into two tasks. So the first one is basically the micromechanical modeling of failure. So I'm going to discuss a little bit about the kind of material model that we have used, the kind of tools that we have used to model fracture. And then, since the kind of tools that we use for modeling fracture, which I'm going to say is going to be like a phase field model, there are very important mesh requirements to solve a phase field problem in such a big domain. So we have also tried to answer that in terms of the computational bottleneck that phase field problems typically face. And we have kind of proposed a solution for that as well. So these are the kind of the two main topics that I'm going to talk about today. So starting with the micromechanical modeling of failure, as I said, this is a highly coupled problem, multiphysics in nature, because you have deformation fields, which are mechanical fields, essentially the mechanical problem that you are solving, given a load, trying to understand how the material deforms. Since the properties of the material is such that it also generates electrical fields because of the piezoelectric nature of the material itself, there is an electrical problem that has to be solved in conjunction with the mechanical problem. And the material is undergoing huge amount of damage because of these electromechanical loading states. So there is a damage problem that has to be solved. So we are concurrently solving for these three problems together in this setting. Now, the kind of damage mechanisms that we are looking at in these piezoelectric composites, again, are typical composite failure mechanisms like debonding between the fiber matrix phases, matrix cracking, which is like a consequence of the debonding itself, and fiber breakage. Although for our problems, we did not observe fiber breakage, but the model is generalizable in that condition, in that way, so that we can also model fiber breakage. This is the mechanical part of the problem. The electrical part is again an interesting phenomena that we observe. Since there are gaps that are created because of the propagating cracks. Now, these cracks mechanically do not mean anything because it's just air that is filled, air or some kind of a liquid that you might use to conduct these experiments in. But electrically, these crack gaps are very interesting. These crack gaps basically act as capacitors. You could say that there are two heavily charged surfaces around that crack gap, and that those high charges basically propagate into the crack gap in the form of very high electric fields. So that is like a singularity in the problem itself, and that is something that we want to resolve as well, because that electrical field is what we want to read later on. That is the electrical signature that tells us how the damage is propagating overall. Okay, so coming to the modeling part of all of this. So we are using a phase field based model to implicitly track all crack paths in the computational domain. That essentially eliminates the need for any cohesive elements because we are using phase field. So standard phase field morphology is what we are using. A phase field order parameter lies between 0 and 1, 0 being intact state and 1 being fully broken. So that is what we are using to model crack initiation as well as propagation. Now, as I said, we are solving for those three problems concurrently. So we have governing equations for each of those. The first one, which is for solving the displacement field or the mechanical problem, which is basically the balance of linear momentum. The second one is solving for the electrical field or the electrical potential in this case, which is basically the Gauss's law that we're trying to solve. And for the phase field or for the damage field, we're trying to solve an Allen-Kant type governing equation where the phase field is an evolving variable and it evolves given a certain certain state of mechanical energy. So these three problems, as you can see, they are highly coupled and they have to be solved concurrently. So that's basically what we are trying to do in the rest of this work. Now, since we are dealing with interfaces, since we have like two distinct phases in the material, we are dealing with interfaces. We also need a way to resolve the features of the interface itself. So what we have proposed here is a cohesive zone-based phase field approach, where we resolve the interfaces as well as, just like the way we resolve phase field with an order parameter S, we call it here, that lies between 0 and 1. It's a smooth function between 0 and 1. We also resolve the interfaces with an interface phase field order parameter, eta, which also lies between 0 and 1. And that basically, it's a field variable defined everywhere in the domain. 1 at the interfaces, the value of that field is 1 at the interfaces, and it slowly moves to 0 over a certain length scale. So just analogous to the gamma function that we typically use for to give us the energy dissipation or the energy required to create crack gaps, like the Griffith kind of an energy. We also introduce a functional that is written in terms of the interface phase field order parameter that tells us about the energies at the interfaces. And so this next slide basically talks about the kinematics of the problem. Now, given that we have demarcated interfaces everywhere in the domain, So the displacement of the potential field is basically divided into two quantities. One is the continuous field, which is continuous over the domain. And then there is a jump in both of these fields because of the interface, because of this opening of these crack gaps. Now, I'm not going to discuss the entire mathematics, but we can derive the total deformation gradient into an elastic part and a damaged part, given that we are assuming that the displacement of the potential field is divided into a continuous part and a discontinuous part. So this is how we perform a multiplicative decomposition of the deformation gradient. And if you go through the math, you can actually calculate the damaged part of the deformation gradient or discontinuous part of the deformation gradient from the total deformation gradient itself, given what point you are on in the domain. So that point basically tells us the state of the interface phase field order parameter and its gradient, which basically tells us what that discontinuous part of the deformation gradient is going to be. That also tells us what these two parameters right here are going to be, which is basically a normal separation and a tangential separation. These are quantities that you typically use to model cohesive zone based models. So these two quantities along with a cohesive zone potential function basically tells you how the interfaces react to different kinds of loading. So that basically gives us like traction separation laws at the interfaces. Looking at the constitutive model itself, there are, since we have these two phases, the inclusions are the fibers, which are piezoelectric in nature, and the matrix, which is like a soft dielectric matrix. We have two different Gibbs energy functionals that describe the constitutive behavior of each of those materials. So for the, let's say for the piezoelectric fibers is what we show first, is we use like a quasi-linear kind of a material. So we have a fourth order elastic tensor that defines the stiffness of the material itself. And for the matrix, since it's a soft dielectric matrix, we use like a neo-Hookean material model to model the dielectric behavior or the matrix behavior of the second phase. Now, since this is a damage problem, we need to divide, or we need to disintegrate our energies into tensile and compressive parts. We have a very nice way of doing it. I would really suggest you to go through this paper. So we basically divide this energy into the tensile and the compressive part to make sure that we have the tension compression asymmetry in the system. Apart from the mechanical energies, we also have the piezoelectric energy and the dielectric energies. The piezoelectric energy is just like a linear coupling between the electrical and the mechanical fields. For the dielectric energy, it's completely based out of the gradient of the potential field or the electric field itself. And you have some phase field, some degradation function as a part of all of these energies, because as phase field evolves or as damage evolves, all of these energies are going to overall decrease, because these are stored energies that are going to decrease, and that energy is going to be dissipated. So that's how any fracture mechanism would evolve. The fourth part of the energy, which is the crack surface energy, is a little interesting in this aspect, because we have two phenomena that are basically affecting the fracture behavior. One is like a Griffith type fracture, which only occurs in the matrix. And then there is an interfacial debonding kind of fracture mechanism, which occurs at the interfaces. So if you look at these two terms of the energy, the first term basically gives us like a Griffith kind of an energy that is required to create new surfaces in the matrix or in one of the faces itself. And you see this function 1 minus eta square. So wherever eta is equal to 1, which is basically very close to the interface, you would see that this energy is going to be 0. So that means the contributing energy is the second term. which is basically the interfacial debonding energy. Whereas far away from the interfaces into the deep into the matrix or deep into the fiber, the first term is going to be dominant because eta is pretty much close to 0. So you have this GC times gamma LC, which is the dominant energy term in that case, and the second term just goes to 0. So this is the way we divide our crack surface energy into these two distinct terms, and this uh, uh, auxiliary parameter of the interface phase field order parameter basically helps us in distinguishing which part of the energy is going to be dominant at every integration point or at every material point in the domain. And then, of course, we have the constitutive relations for the first Piezo-Kirchhoff stress and the electric flux from the derivatives of these energies in terms of the deformation gradient or the electric field. So this is essentially the entire constitutive model for this material. The second part that starts now is basically talks about the computational bottleneck that we typically have with phase field problems in general. So the issue with phase field problems is that the mesh requirement is pretty high in terms of that you have a critical element size based on the length scale parameter that you use for phase field to describe the phase field evolution of damage in the domain. So that high mesh resolution essentially leads to very high computational cost because you need to refine the mesh very fine wherever you may expect cracks. That also leads to slower convergence rates because of the way the phase field order parameter is set. It is supposed to be a very high gradient field, so it very sharply drops from 1 to 0 within that small length scale. So that essentially leads to a lower convergence rate for the solution field itself. So let's see, like we are looking at a typical mesh that we would require to model a crack that looks something like this on the right hand side. And the mesh is refined selectively in the region where you would expect the cracks to evolve. But if you use a very coarse mesh and want to resolve the cracks in that small length scale, we are going to get results that are not physical. As you can see, it's that's not how the crack would look like, or you would expect the crack to look like. So we wanted to have an efficient way of dealing with this issue. So what we came up with is an adaptive hierarchical finite element framework for this. So typically, hierarchical finite elements are very good in resolving high gradient fields. So where the solution variable, for example, here the displacement is basically divided into two components. One is called the core solution, which is typically your standard shape functions times the nodal value of the displacement variable itself, and a fine solution, which basically adds a correction to your entire solution field. So if you look at the figure on the right, these n1, n2, n3, which are in color, these are like the standard shape functions that you would use for, let's say, these two elements, x1, x2, and x2, x3. But you can also add these extra nodes, x4 and x5, where you can define a fine shape function that adds to the correction. So if you look at the nodal values at these points, which are basically like corrections to the solution field itself. So in the absence of these corrections, you would get a field solution that looks like this gray line over here. But in the presence of these extra fine shape functions, now you can add corrections to the solution variable itself, and that gives you better resolution of the solution field. And and so if you want to solve the problem using this, then you typically have different degrees of freedom for the coarse part of the solution field and the fine part of the solution field, and that this is how you would want to solve the stiffness matrices and the right hand side force vector. Now, we still need to know where to put these these fine shape functions. So we still need to know where to add these hierarchical nodes in the domain itself. So to understand that, or to solve that problem, we use a hierarchical, wavelet-based approach. So what we usually do is use a certain category of wavelets to tell us where to put those additional fine scale shape functions or fine scale nodes, hierarchical nodes in the domain. So just a brief introduction of wavelets. So it's something like, if you're familiar with Fourier type expansions, the wavelets are also something similar, but they have the main advantage of wavelets over Fourier type expansions is that wavelets have a compact support. So it fits very well in the finite element framework, because finite element shape functions also have compact support. So this essentially can deal with any kind of Gibbs phenomena that typically occurs with FFT or fast Fourier transform based solvers. So I'm not going to go into the detailed mathematics of it, but what we typically use are called these second generation wavelet basis functions that are constructed out of the standard shape functions itself. That therefore they fit very well into this finite element framework, because the shape functions and the wavelet basis functions are kind of constructed from the same basis functions. Now, how would you still tell us where to put these hierarchical nodes? So for that, we define an error indicator. Since we do not need the exact error, or we cannot actually calculate the exact error just from finite element solutions, what we proposed here is an error indicator, which tells us, which gives us regions in the domain where the error is going to be high. So we want to put our hierarchical nodes in those regions. Now, this error indicator is calculated basically from a set of standard finite element shape functions and a set of these hierarchical nodes that we know already in the for solving a particular time step, and then project that solution onto a lower scale set of hierarchical nodes that we want it to be true. So if you can if you go into the mathematics, you can definitely look at these papers which deal into much details of the mathematics of it. But essentially, what we are doing is projecting this error indicator into that wavelet basis that we discussed in the previous slide. Now, by doing that, we can find these wavelet coefficients which are significant. Once we have decomposed the error into the wavelet basis functions, we can find out which nodes or which hierarchical nodes are important given a certain threshold on the wavelet coefficients itself that you get from this wavelet analysis. So given a certain threshold, or a certain threshold that this error has on the wavelet coefficients, you can put the hierarchical nodes in those locations where that threshold is met. So that is typically how you would do that. And once that is set, now you can say that, okay, these are going to be my standard shape functions, these are going to be my hierarchical shape functions, and then you're going to resolve the solution field, be it displacement or the electric potential field or the phase field into the solution. So that is typically how we take care of this entire adaptive framework using this wavelet basis functions or the wavelet analysis. So now, since we have used this, it provides very nice properties of the solution itself. It will be able to resolve the high gradients in the phase field order parameter, and you will see how those results look like. These, since we are using a hierarchical framework, you do not have to remesh that you would typically do for a remeshing kind of like a remeshing technique that you would use typically for these problems, since this is like a time evolving problem where the cracks are moving into every area of the domain. So you would not have to do a remeshing. So you can preserve the coarse mesh and use those coarse finite element shape functions into the hierarchical framework itself. This wavelet basis also, since it conforms very well with the solution because of the compact support nature of the problem itself. So it allows a very nice framework to be used alongside with finite element in the finite element context. And it provides actually will show in the results that it provides better convergence as compared to like other edge refinement techniques. So now looking at the same problem again, the 2D single fiber problem that we showed. Now even with the coarse mesh, we are able to adaptively add these hierarchical nodes as the loading progresses. And because of those hierarchical nodes, now we can see a very nice phase field order parameter, a very sharp region of the phase field where the phase field grows, even with the very coarse mesh to begin with. So this provides us the flexibility of using this technique for larger systems where the cracks can grow very randomly. So you would not know where to provide fine refinement if you wanted to begin with a very refined mesh to solve the problem. Some examples that we show here. The first one is like a double cantilever beam. So we have an interface, as you can see, running right in the middle of the beam, and you have a notch. So it's like a mode 1 fracture kind of a problem, and you also apply some electric potential across the two interfaces. Now, since we are doing this with the hierarchical framework that I just discussed, we also see that the convergence properties are much better. It converges much faster. If you can see, the blue line has a much steeper slope as compared to a standard like a hierarchical edge refinement or even remeshing techniques. It does show better convergence. And you are able to resolve a very narrow crack, a very thin crack in the domain, as well as look at the strong discontinuity in the electric potential because of the presence of this thin crack with a very coarse mesh. This is again another problem, which is still a simplified problem, very ordered fiber composite matrix. It's a piezo-composite matrix again. So you can see that as the phase field evolves, how the enrichment nodes or the hierarchical nodes are also being put in locations where the phase field is expected to grow. This happens like automatically because of the algorithm that we use, the hierarchical or the adaptive wavelet-based algorithm that we use. So just to compare with how it compares with the standard finite element technique. So to solve this kind of a problem, we have tried out with approximately 115,000 degrees of freedom. And to begin with, so it's a standard FEM, already used a refined mesh, since here we know how the crack is going to evolve. So we can do that for the sake of comparison. And for the proposed FEM, we can solve that with way lower degrees of freedom. So it's approximately around 40,000 degrees of freedom. And you can see the difference in time that is taken to solve for one load increment. So it's like almost, I would say, a little more than half. So about 60% of what you would use for a standard FEM. So yeah, the goal was to use it for a more complicated microstructure where we would not know how the cracks would evolve. So this is an example of that. We have like a randomly distributed fiber matrix microstructure. We apply a mechanical load as well as an electrical field. Hard piezoelectric fibers that are poled in the y direction, and soft dielectric matrix. And we also compare how the number of degrees of freedom look like, and the average time for load increment. So yeah, So here as well, you can see it's like almost, I would say, less than half number of degrees of freedom that are sufficient to resolve these sharp cracks. And you can also see how the convergence rates compare as compared with a standard hierarchical refinement strategy. So yeah, I think with that, I would like to summarize that this has been a good experience working with some good material models as well as a good computational strategy to solve this issue of phase field mesh requirement, as well as a constitutive model that takes care of a lot of fracture mechanisms, both electrically and mechanically. So yeah, that's my talk. I would love to answer any questions. Yeah, please go ahead.
Thank you so much for these great presentations for such a solid works. I do have a few questions to ask.
Sure.
The first question is, I see you show a cross-grain mesh with the wavelet enhancement. So for each mesh, do you only add one additional point implement with the wavelet basis, or you can add as much as point as you want in the developing process?
Yeah, you can add as many points as needed. So essentially, with the coarse mesh and length scale order parameter, a length scale parameter that you require for the phase field order parameter, those are the two kind of inputs that are required for this solution process. And the wavelet basis automatically detects how close those hierarchical nodes are required to be put. So that is something that the wavelet basis or the wavelet algorithm itself does. So it automatically puts multiple nodes at a time for every time step and for every wavelet enrichment iteration. So yeah, it's not necessary that you only add one node at a time. You can add multiple nodes at a time based on the requirement of the phase field problem itself.
Yes, and also many nodes in the same element.
Yeah, exactly.
Great. Yes. And there is another question. Does the fracture in your model is driven by both the mechanical energies and the electric energies?
Yes, it is driven by both. But if you want to induce fracture just by applying an electric field, you would need a very high electric field to provide those deformations for the material to actually fail. So it is mainly dominated by the mechanical fields, by the mechanical load. But yes, it can also be initiated by electrical loads because of the piezoelectric nature of the problem. If you can apply a very high electric field that actually induces mechanical deformation, and fracture can occur because of that as well. So the model takes care of that. Yes.
Yeah, great. So to my understanding, this model can capture the transition of the fracture development from the mode 1 to mode 2.
Yeah, it
Or
can.
something else. Yeah. Oh, great.
Yeah.
Nice work. And also, or maybe someone other people has questions.
Yeah, great presentation, Saikat. So for Yaron's question, I think I have asked this question before. At the portion of the piezoelectric energy and the mechanical energy.
Mm-hmm.
I think we get the idea from Professor Wu's paper, right?
Yeah.
So he actually managed to calculate that fraction. Yeah, here you can see.
Yeah.
So this portion is being calculated, and but I think I think you can also put different fraction here to test.
Yeah.
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 And also for the mode 2 loading case, do you actually have such case, mode 2 loading case?
We tested like standard specimens of mode 1 and mode 2. So like you would have like a rectangular or a square domain with an initial crack, and you would load it in mode 2. We have tested those out. I do not have them in this presentation or in any paper, but yeah, we have tested it out with both mode 1 and mode 2, especially without the consideration of interfaces. So with the consideration of interfaces, we have only done this mode 1 test that I showed, but mode 2 has been conducted with without the consideration of interfaces. That is something that we have tested it out. We don't have it on any paper, unfortunately.
That's also my impression, because I have in your thesis, I think you compared the simulation result to the experiments only for
Mode 1.
The mode 1, and it's the full domain is piezoelectric.
Yeah, full domain is piezoelectric. Yeah, I mean
that's also one difficulty, because it's really hard to find any experiments that's actually on the composites.
Yeah, you answered my question. Yeah.
yeah. Anyway, that's all. Thank you.
Yeah, thank you so much.
Yes, great work. And small questions. How do you come up with the cohesive Zufrak phase-field models?
Well, I think it was so the cohesive zone model, like typically with cohesive zone models, you would have cohesive zone elements, right?
Yeah.
So cohesive elements that are added wherever you want them to be. But the problem, we actually started with that idea, but the problem there would be over what I'm showing right now in this slide. So because we are not just solving the mechanical problem, we're also solving the electrical problem. And for the electrical problem, the crack gap is just not a gap. So you cannot just resolve everything on the cohesive surfaces. You also need to integrate stuff in the crack gap itself. So you see this right-hand side of the energy, this part where what I'm pointing to. This is like a this is like a capacitor energy that needs to be integrated in the crack gap itself. So cohesive elements only integrate stuff on the surfaces, on the two cohesive surfaces. So we wanted to use this phase field framework as well, and we wanted to have it like in a unified way. So we didn't want to use again a set of cohesive elements and then phase field for the fracture in the like in the matrix, and then the cohesive elements to understand the debonding characteristics. So we wanted to do that in one complete framework, as well as have this capability of integrating stuff in the crack gap. So I think it was from like one of the papers that we took the initial idea from, and then we developed this for like finite deformation, and then with multiple fields and things like that. So yeah, this is like a very nice collaborative work. I should really say that this has been a nice collaborative work between me and my other friend who was a graduate student along with me. So yeah.
Okay, yeah, but here I still have to point out one thing, that here the cohesive zone should be already known a priori.
Yeah. It has to be already known a priori. Yeah, that's true.
Yeah.
Does anyone has further questions? Well, thank you so much for coming to today's student chapter seminars and the nice talks. It's really impressive. Thank you so much.
Thank you so much. Yeah, thank you for the invitation. Yeah, really appreciate it.
You're